Okay, so let us start the final session of this afternoon. So the speaker is, we are very happy to introduce the speaker, Ignacio Cirac from, from Munich, Max Planck Institute. And he will tell us about quantum circuits, cellular automata, and tensor network. Please start.
Okay, so thank you very much and good afternoon to everybody. It's my pleasure to be here remotely. And so the first thing that I want to do is to thank the organizer for this very kind invitation. So I hope that next time or in the future I can be there in presence, but nevertheless, I'm also very happy that I can give this talk yes, by video conference. So I'm going to talk about quantum circuits, cellular automata, and tensor networks, and that's a work that I've been carrying out during the last couple of years, especially with two postdocs in my group, Lorenzo Piroli and Giorgio Stiliaris. So Lorenzo is now in France in ENS, and Giorgio is still a postdoc at MPQ, and it's based, like many of our work, on tensor network on some very long-standing collaborations with David Perez Garcia, Norbert Schulk, and Frank Festrati. So I know that this conference, this workshop, actually, it's a very broad audience coming from many areas. And so I'm going to talk about something that I think that is connected, especially to quantum information and a little bit to condensed metaphysics, and also because that I'm to some extent to more broad sense of quantum information and connections to quantum gravity. But probably I think that I would concentrate on the quantum information side. So in the title, I gave three names, quantum circuits, quantum cellular automata, and tensor networks. And as you will see, the common property of these three things is that I will use them to represent unitary operators, to represent the dynamics or the evolution of a system. So you know very well quantum circuits because these appear in quantum computation, for example, or also when one wants to study the complexity of states. So what's the cost of preparing certain quantum state in a many-body physics? Maybe you're familiar with cellular automata, and they were introduced many years ago in the classical setup to describe with some local rules, so possible dynamics, complex dynamics of systems, and a quantum cellular automata, as I will show. It's a quantum version of that, but it's defined now with a different aim. So the aim is to define the most general unitary operator that keeps causality, or that keeps locality, that preserves causality and locality. And so it's a very general statement, or general, let's say, definition, but we will see that it's somehow connected to quantum circuits. And the last one is tensor networks. So tensor networks have appeared in different areas in physics, quantum information, condensed matter, and also high energy physics, and even in quantum gravity. And so these are ways of describing with simple tensors many-body operators. And so as we will see, these tensor networks also have some kind of locality in them, in which they are defined locally. So it will be defining with a local tensor, a tensor that represents something in some position in space, and then you just concatenate this tensor. And if you do that, then they can give rise to some dynamics that maybe this keeps in some way this locality. But as you see, these are the three different definitions. And so what I want to do is to establish the relation. And once I have established the relation, so to see what are the consequences of that, and also to extend some of these definitions to make them useful in the field of quantum computation, or in the field, as we will see, of classification of phases of matter. So let me start with quantum circuits. Very simple. So this is what is typically drawn when you have a quantum circuit. So you have a set of qubits which are represented on the left, and now these qubits evolve in time from left to right, and each of the lines represents the life of one of these qubits. And in a quantum circuit, what you have are two qubit gates that are just connecting two qubits sequentially. So first there are some 2 qubit gates, and another set of 2 qubit gates, another set of 2 qubit gates. And so this, at the end, you will have apply some unitary operation to the qubits, because each of the qubit gate is unitary, and therefore the concatenation of these unitary operations is also a unitary operation. And so what will be important for what I will discuss later on is the concept of a layer. So you can divide a quantum circuit in different layers, and each layer is defined because one qubit in a layer interacts once with the nearest neighbor to the left and once to the nearest neighbor to the right. And if you are in higher dimensions, then in a layer, they interact each qubit once with each of the nearest neighbors. So therefore, the whole quantum circuits can be divided into layers. So for example, this here would have 4 layers, and the number of layers in the language of quantum computation is called the circuit depth of the quantum circuit. Now, quantum circuits appear, as I mentioned, in the field of quantum information and also in the field of condensed matter physics. And let me just revise what is the motivation in quantum information. So in quantum information, a typical question is given a quantum computation, given a unitary operation. So what is the circuit depth corresponding to that? So you're giving me some quantum computation. So for example, Shor's algorithm or any other algorithm that solves a problem in a quantum computer. And then you would like to know if you decompose it into a quantum circuit, so how many layers you will have to write. And of course, basically, the number of layers is related to the computational time. So this question that I asked, so what is the circuit depth of a quantum computation, is nothing else. So what is the time that it would take to run the circuit on a quantum computer, as long as you can, like in this case, run each of the layers and for each of the qubits in parallel. So you can apply the gates in parallel, which in quantum computers, if we want to make them scalable, that's a requirement. Now, in general, it's very difficult to answer this question. And so what you can do is very easily to put upper bounds. So you just find the composition of your unitary operation in terms of a quantum circuit, and this automatically gives you an upper bound to the depth of your circuit. However, there are infinitely many decompositions of the same unitary operation. You can even have the identity operator, the most trivial operator that you write as a U dagger, an very complex circuit, and then the inverse of the circuit, and this would be a quantum circuit itself. Of course, this is a very inefficient way of doing nothing, of just applying the identity operator, but the same happens with any unitary operator. You can write in terms of many gates or sometimes few gates, and so it's easy to find upper bounds, but it's more difficult to find lower bounds or to find the optimal, let's say, depth for a quantum, for a unitary operation. So regarding lower bounds, I mean, sometimes it's indeed possible, and here is an example. So this is a unitary operator, which is the identity plus I time, and then Pauli sigma x operators acting on the rest of the qubits. And the reason why this, I mean, the depth, you can show that is larger or equal than n-1, where n is the number of qubits. And the reason why you can prove it is very easy, as because first of all, you see that out of the if you start with a product state, then you will be able to create a GHZ state. So you will be able to create the state 0, 0, 0 plus I times 1, 1, 1, 1, 1. And that state has a long range correlation. So any qubit is correlated to any qubit. So if I measure one qubit in 0, then the nth qubit, if I measure it again, it will also be in 0. However, you can also show that in a quantum circuit like this one here, in each layer, you can only increase the correlation length by 1. And therefore, you have something that has correlation length n, then this means that you will all be able to have a correlation of a quantum, a depth of the circuit should be larger than some number. In this case, is n-1 if you do a bit more sophisticated statement. Anyway, so of course, as I mentioned before, the depth of a quantum circuit depends on the dimensionality. So you go now to current implementations of quantum computers, or some of them are one-dimensional implementations, and that's what I was drawing, some layers that have taken into account the one-dimensional geometry of your system. You can have a two-dimension, like this happens, for example, with the Google quantum computer, or with, let's say, Rydberg atoms in tweezers, if they interact with nearest neighbors. And then, each layer is composed of 4 steps, as you can, is represented here. And then there are some other implementations of quantum computation in which you have all-to-all interactions. So you can do gates between any pair of qubits. And then in that case, the concept of layer is different as well from the other cases. So there's something that has to be taken into account, and I'll mention that later on. Okay, so now let me tell you a little bit about how quantum circuits enter in the world of many-body physics. And so one way in which they enter is when you ask questions like, are two states in the same phase of matter? So you have a many-body state, for example, on a lattice, and another many-body state in the same lattice, psi and psi. And you want to establish an equivalence relation that tells you that two states are related to each other and they are in the same phase of matter. And what basically it means that they have basically the same non-local properties. So that's what I mentioned before. So that the classification of phases of matters is related to an equivalence relation, and this equivalence relation is defined in terms of the depth of a quantum circuit. So you say that two states are equivalent if there is a low depth quantum circuits that connect them. So maybe more explicitly, so state psi and phi are in the same phase of matter, are related if there is a quantum circuit in which the depth is low depth. And of course, now what does it mean low depth? So typically in condensed matter, you're interested in the thermodynamical limit. So you have to scale the depth of the circuit with the size of the system. And so what you ask is that the size of the depth of the circuit should scale subpolynomially with respect to the number of qubits. So this means basically that these two states, can be transformed more or less into each other just with some local operations that are acting only on qubits, but with very few layers of a quantum circuits. And of course, there are many details into that. So how to take the limits, and also, maybe you don't want to do it exactly, but approximate it as a here. And of course, then there's a lot of mathematics related to that. But I can see that the concept, it's very clear why quantum circuits are important in order to define an equivalence relation in condensed matter physics. So this means at the end that the set of states now will be divided into classes, and in each of the classes, then since the states are related by some small depth quantum circuits, then we'll have very similar properties related to correlation functions and things like that. So that gets more interesting if now you restrict yourself to spatially relevant states. And these spatially relevant states are ground states of local and gap Hamiltonian. So you have a Hamiltonian defined in the lattice, and you can write the Hamiltonian as a sum of terms that are geometrically local. So just acting on few, let's say, quantum systems around some point. And you're looking at the ground state, and it turns out that there is a gap in the Hamiltonian. So there is an energy gap between the ground state and the first excited state, even in the thermodynamic limit. And you can apply this equivalence relation that I mentioned before. And so many people have studied then, so what are the phases of matter now for ground states of local gap Hamiltonians? And the result is here that in one dimension, so you have a one-dimensional system, and then the number of phases is equal to the degeneracy of the ground state. So for example, you have ground states, you have Hamiltonians that have unique ground states, then there is a single phase. So what it means is that you can prepare any state just with let's say a low depth circuit connecting to the state 0, 0, 0, 0, 0, 0, 0. So basically all the states in one dimensions are the same according to this classification. Now you have the degeneracy 2, so if there are 2 ground states, then of course this is connected to anything that has 2 ground states, like for example the GHZ state. It's or you have a Hamiltonian for which the ground state is the GHZ state, then actually there are 2, the degeneracy is 2, and it is connected to any other Hamiltonian, or this phase is the same as the one that would correspond to any other Hamiltonian that has the degeneracy 2. Now, in 2-dimensional systems, the situation is very different, because even if for a given degeneracy, there are many different phases and they correspond to topological phases. And so this has attracted a lot of attention in condensed matter physics, because it means that even states that can be prepared in experiments, then you would need a circuit depth that grows linearly with the size of your system. And so that has some physical consequences. Now, some other people have gone beyond and have studied, so what happens when you impose symmetries in your state? So your Hamiltonian has some global symmetries. And in that case, if you want that your unitary, so your quantum circuit respects the symmetry, then you have a finer classification. And these are what is called symmetry protected topological phases. And for example, on one dimension, if the degeneracy is equal to 1, instead of having a single phase, you may have many phases depending on the symmetry. Okay, so this was the first part, the quantum circuits, the first kind of unitary operators. Let me move to the second one. These are quantum cellular automata. And so cellular automata, you are very well known, and so it's, for example, in the game of life, they appear. And the definition is that this is evolutions in say lattice, with there is some geometry like the one that you see on your screen, in which this evolution in time steps is defined in terms of local rules. So when you have two black dots in the screen, then in the next step, then with certain probability, maybe I mean, out of the two blacks, and there is only one black, or there are three ones appear. So you define a set of local rules, and then you evolve with these local rules. And what you see is that depending on the initial conditions, you can evolve in very complex structures. And so people have figured out that many processes can be defined in terms of cellular automata, can even have gains based on cellular automata. And people have also shown that they give rise to a universal classical computation, meaning that if you just prepare a different state and then you let it evolve, then this can solve any computation, and the complexity of the computation doesn't change as compared to the circuit model of computation or the Turing machine. Now, in the early 80s, so people tried to extend this definition to the quantum realm, and the motivation at that time was purely curiosity, or because people were thinking about quantum computation, and they wanted to see also if a quantum cellular automata would be universal, would be as powerful as a quantum computer defined in terms of quantum circuits. And there are many definitions of quantum cellular automata, but all of them at the beginning confronted with the fact that it was very difficult to impose locally the constraints or the rules of the game. Because, for example, if you want to have some translationally invariance, you want to keep the homogeneity of your system, if you define something occurring on one side, and then you had to define something in the next boring size, and the operators which define the evolution of this size don't commute with each other, this brought some problems in the definitions to make them translationally invariant. And the solution came in these later papers of Arrighi, Nesme, and Werner, where they have what I think that today is accepted as a definition of quantum cellular automata, which goes away from the extension of a classical automata. It takes a more general point of view. And this more general point of view is that it defines a quantum cellular automata as the one that in the Heisenberg picture transforms operators acting in some regions, in some operators acting on that region plus a little bit. So this is what is represented here. Imagine that you have an operator X, which is supported in some region A, meaning that it doesn't act in the rest. So it's the identity operator acting on the rest, but it's only here. So for example, this could be a single qubit Pauli operator. And now if you evolve with a quantum cellular automata, then it will be an operator which now is supported a little bit further, where R is what is called the range of the quantum cellular automata. And so this is a very general definition, and any unitary operator which fulfills this property that, keeps this kind of locality, then it's called a quantum cellular automata. So as you will see later on, I want to make a connection between quantum cellular automata and quantum circuits, but I want to introduce yet another kind of unitary operators, which somehow are defined in terms of some local rules, and these are based on tensor networks. So I think that most of you are already familiar with tensor networks, but let me summarize in a couple of slides what the tensor network is. So we have a set of qubits or qubits like before, and now we can write any state in the computational basis, and we write the state in the computational basis, then all the information about the state will be in the coefficients in the computational basis, which can be considered as a tensor which has n indices, with n is the number of qubits. And so we represent this tensor in terms of some block with some legs that corresponds to each of the indices. Now you can also have an operator that is acting on the qubits, and you can write it also in the computational basis or in the 0-1 basis, in the eigenbasis of sigma z operators. And the coefficients now, then they will also have a lot of indices corresponding to the brass and the kets of the operator. And this can also be considered as a tensor with many indices. And so we can represent it also as a block that has some indices to the left. This corresponds to the ket indices, and some indices to the right, the bra indices. And so we represent it like that. And whenever we compute some expectation value, So what we will have to do, you just use these definitions, is you will write it as a contraction of tensor. So you see here, you have the tensor corresponding to psi, then the tensor corresponding to x, the tensor corresponding to psi, again, complex conjugated. And now you start contracting indices because this is the multiplication that you have to do. And this can be represented now in this tensor network language as a block corresponding to the tensor C, then the block dx, the tensor C conjugated, and now the indices that are first identified and then sum over are represented just by joining these blocks. So that's a language that one uses with tensor networks, and it turns out that it's very clear that when you have quantum many-body systems, I mean, you automatically, if you write things on a specific basis, then you have to deal with tensors. Now, what is interesting in our context, it is now, if you concentrate now on operators that are unitary operators, because that's the content of this talk. And in particular, when you have unitary operators, then there are some famous tensor networks that describe unitary operators. Some of them are called matrix product unitary operators, in which the tensor, which has now these bra and ket indices, is decomposed in smaller tensors of this particular form. And from now on, and when I talk about tensors, I will consider translational invariant operators, and this means that these tensors will be the same, and if you want, you will have periodic boundary conditions, so the last tensor is joined to the first one. And so we typically call the indices that go out, so the original indices of the original tensors, the bra-ket tensors, physical indices, and these other tensors that now in which we decompose this big tensor in terms of smaller tensors, we call auxiliary indices. So the big tensor network, unitary operators describing terms of small tensor networks which are contracted along the these auxiliary indices, and the dimensions of these bonds. So it's related. So these indices here, these auxiliary indices, will run from 1 to some number, and this number is called the bond dimension of the tensor network. You can have also two-dimensional or three-dimensional versions of tensor networks on this form, in which again you're giving a tensor, and then you tile it up, given the structure, the geometry of your space, and then you connect them. And this, if it represents a unitary operator, then you call Pepus or projected entangled pair unitary states. Pep unitaries. And so what is peculiar for tensor networks, and this is why they make them so attractive, is that even you have a huge Hilbert space, you have the dimension of Hilbert space grows exponentially with the number of qubits or of qubits, still the description does not require this exponential number of coefficients, because now it's encoded in small tensors. And so, for example, you have translational invariance, like I mentioned here. Just if I give you a single tensor, this specifies completely the whole unitary operator in any dimension. So maybe this tensor, you see, has the physical dimension. These are qubits, this is 2, and it has this auxiliary dimension. Imagine that is also 2. So only with, in this case, would be 2 to the 4 times 10 to the 2. So something like 32 parameters. No, this is 2 to the 6. Okay, so it's 64 parameters. Then you will describe all possible unitary operators that are corresponding to this bond dimension 2. So again, independent of the size of the Hilbert space, with a single tensor, you describe the whole operator. And as you see, somehow one can see that in the definition, there is some kind of locality, because you put each tensor at each place where geometrically each of the qubits or each of the qubits is sitting. And so therefore there is some locality, but the question is, what is this locality related to the other, the localities of the other definitions that I gave about unitary transformations? And so now what I will show is that the quantum circuit with depth 1 and the quantum cellular automata, let's say with the range is equal to 1, and the tensor networks, which have some bond dimension C, where C is basically, some D times the coordination number, they fulfill this relation. So each contain each other. And this is also true now. You have more layers, but I just concentrate on a single layer. But let me show that, because it's relatively simple. And so this makes the connection among them, or one connection, and later on I will make more connections. So the first thing is that why quantum circuits are included in the set of quantum cellular automata. that's trivial to prove, because we just have to prove that if we take an operator just acting in 1 qubit, let's say, like here, and then we apply U and U dagger. So as I mentioned before, in the Heisenberg picture, then the result of doing that is an operator which is supported in a small region around the original qubit, where the original qubit was set. But as you see, so now we have the quantum circuits. These are some unitary operators. These are the daggers, the unitary operators, and you see that here you have U dagger U. So you can cancel this. You can cancel this, or you can cancel several unitary operators, like the ones that are here in the cross, because they are not affected by the fact that we apply the operator O there. And now you can see that on the next layer, this operator and this operator can also cancel, because this is some U and U dagger, and this U and U dagger can also cancel. So as you see, the operator O now is just supported in the 4 qubits that are, or 3 qubits that are around the original, and therefore this is still local. And according to the definition that we gave before, then this means that the quantum circuits are indeed in the set of quantum cellular automata. So I give you a quantum circuit, and then it's also a quantum cellular automata. Now, the fact that this inclusion is strict, it's proven by the following example that was given in this paper here, and that's the shift operator. So imagine that is an operator which takes each qubit and moves the state once to the right, and consider periodic boundary conditions. So that's what is represented here. So it's very simple to show that this is a quantum cellular automata, because if you just put an operator acting here, it will only shift it in the Heisenberg picture, I mean, once to the right, so it will be supported around the original region. However, it's very simple also to prove that if you try to build a unitary operator which makes this shift with a quantum circuit, then the depth of the circuit will be proportional to the size of your system. So it will be n, if you have n qubits. So this shows indeed that there is a quantum cellular automata that is not a quantum circuit. Okay, so now the other is that the quantum cellular automata is a tensor networks, and there are different ways of proving that. Let me just show you ones that uses some tools of quantum information theory, as well as some tools of tensor networks. And so the idea is to consider qubits, just to make it simple, and just make an auxiliary construction. So what we are going to do is, with this auxiliary construction, is to build what is called the choice state, in the way, the choice state corresponding to the quantum cellular automata. So we are giving a quantum cellular automata. We want to show that is a tensor network. And so the idea is what I show here. You just take the qubits in which the cellular automata is acting in any dimension. So I do it in 1 dimension, but anyway, then you consider a set of ancillas or auxiliary qubits, and you consider an initial state in which each of the qubit is maximally entangled with its ancilla. So that's the state that is represented here. And notice that this state now, this joint state of the system and the auxiliary systems, is annihilated by any projector operator. So you put here a projector operator that projects in the orthogonal subspace to the maximally entangled state, then this will annihilate the whole state. So this projector acting on the whole state, on that, will be 0. And also, if it acts on the whole state, it of course will obviously be 0. So that's the first statement. So that actually for this state that we have created, which is very trivial, is a product state of maximally entangled state, there is an operator that annihilates, this projector operator annihilates the state and is completely local. And now we consider the choice state. The choice state is a state that is defined as taking this locally maximally entangled state and apply the unitary operator that we are considering, the quantum cellular automata, only to the system. And at the end, we will have, as a result, some state, as I'm saying, it's called the choice state corresponding to U. And it's very easy to show that this choice state contains all the information of the U. So you would write U in terms of coefficients or in terms of tensors, and it would be exactly, this tensor will appear in this definition. But not only that, you can also show that if this choice state is a tensor network with a small bond dimension, then the unitary, it is also a tensor network, a unitary tensor network, so MPU in this case, with a small bond dimension. So the bond dimension of the operator is exactly the same as the bond dimension of the choice state. So this means that if we have a quantum cellular automata and we can prove that the corresponding choice state is a tensor network, then we have proven that the quantum cellular automata itself is a tensor network. And this can be done in 2 steps. So the first step is just we take the projector that annihilated the original state and conjugate with U dagger. And when we do that, then we see that this is a sum of terms in which each of the projector is conjugated. And since U is a cellular automata and P are local, then this means that these terms here also are local, so are just around the region surrounding the nth qubit. So we have here what we call a Hamiltonian. You will see in a second why it's a Hamiltonian, that is a sum of local Hamiltonians. Now, the second thing is that each term of this Hamiltonian annihilates the choice state, and you can see it right away. So you take UP, U dagger, and act here. The U dagger cancels the U, and then we have the P acting on the psi, but we say that this is 0. So this means that any of these terms, or the whole H, yes, annihilates the choice state. And on top of that, you can show that these HN, so these terms, commute with each other, and the reason is because the P's commute with each other, and by conjugation you don't change this fact. So we have that the choice state is the ground state of a Hamiltonian, which is local and has commuting terms. And one can then resort to the theory of tensor networks, and in that case it was proven already many years ago that then this state can be written as a tensor network with a fixed bond dimension. This shows that the choice state is a tensor network, and this shows that the quantum cellular automata is included in the set of tensor networks. Okay, so now we have the inclusion that I told you before. And now let me introduce a technical property for tensor networks. This is what is called simple. This was introduced in this paper for one-dimensional systems, and this is extension to larger systems. I mean, this is very technical, so you don't have to pay so much attention. Just to take into account that now you have a tensor network that is a unitary operator defined on a lattice in any dimension, and then you take any region A, the boundary of the region A, the boundary of the region A, and the rest. So you divide it in four sides: the region, the boundary of the boundary, and the rest. And if it fulfills that, whenever you have the tensor network, the unitary operator, and then you contract these boundaries and regions, then this disentangle, then you call it simple. So that's a technical condition, and some tensor fulfill that, and it's something that you can check if this is fulfilled even locally. And so it turns out that you can prove, and now it's much more difficult, that in that case, so you have now tensor networks that fulfill this simple condition, and actually they have any equality. So you can also prove that any tensor network fulfilling that condition is a quantum cellular automata, and that any quantum cellular automata is that. So this gives the inequality, and one sees that once you put this technical condition, then you can identify what is the relation between quantum cellular automata and tensor networks. Now, what about quantum circuits? Can we put an extra condition on a quantum circuit in such a way, or give a bit more resources to a quantum circuit in such a way that it's exactly the same as a quantum cellular automata? And then indeed, this is the case. This was also shown in this paper here. And the idea is to add an ancilla and to let the quantum cellular automata, sorry, the quantum circuit, to act not only on the system, but also on the ancillas. If you're allowed to do that, so you're allowed to, put some auxiliary system in some specific state and allow your quantum circuit to act on ancilla, then you can show that the quantum circuit plus ancillas is equal to quantum cellular automata. And the reason is that you can do as follows. So you remember, well, there is a proof, but just to give you an intuition why it is like that, I told you before that the shift operator, it's a quantum cellular automata that is not a quantum circuit. It's not a fixed depth quantum circuit. So let's show that if we have ancillas, now the shift operator can be implemented with a quantum circuit, right? That's what we wanted to show, that by putting the ancillas, then a quantum circuit can do more, and in particular, the shift operator. And the idea is that now what you could use is the quantum cellular automata just to make a swap operator between these two qubits and these two qubits and these two qubits and so on. So as is represented here. So now the state of this qubit is here, and that's what is represented here. So they have moved one to the right and exchange. And then you apply a local operation, and a local operator, if you apply a local operator, this doesn't increase the depth of your circuit, because we are considering that we can incorporate it to the 2-qubit operator. And therefore now the other one just swaps this in this way. And you see that the total result is that this particle here is moved up and then moved to the right, so it has shifted to the right. So you can see that the final state would be like the original state in which you have shifted upwards. You have make a shift of your system, and the ancillas actually are shifted down. But if the state of your ancillas that you prepare is 0, 0, 0, if you shift it down, then it doesn't change because it's already translational invariant. And so that's what I mean shows that the quantum circuit plus an ancilla then can implement any quantum cellular automata. That's an example, but you can prove it in general. And this was what was proven here. Okay, so now we have this I mean, fill out this diagram in which we see that if you put ancillas and if you restrict the set of tensor networks, then they're exactly the same. So now what we have learned that, then we can go a step beyond and say that, well, in quantum information, it's very natural to include also measurements in quantum systems. And so what happens now if we take the quantum circuit, we add ancillas, but we also allowed to do measurements and act on the system depending on the outcome of the measurement. So that's the setup that we have included here. So you have our system again, we have some ancillas. The ancillas are prepared in some particular state. And now you're applying a single layer of a quantum cellular automata and then measure, for example, the ancillas. And depending on the outcomes of the ancillas, they can still apply some local unitary operators to our system. So that's what is represented here. So we start with some initial state, apply cellular automata, measure ancilla, obtain a certain result, and then depending on the result that we have, then we apply some local unitary operators to our system. I mean, in general, this is not a unitary operator because the result that the operation that we apply to our system will depend on the outcome. But it turns out that in some cases, you can apply these unitary operators in such a way that they erase the set of the outcomes. So that looks very artificial or impossible, the fact that you measure something, but you can still correct it independent of the outcome of the measurement, then you have applied exactly the same unitary operator. But I mean, this is not so strange in the context of quantum information. I mean, this happens, for example, in teleportation. In teleportation, you can send a state from one place to another one, and then you make a local measurement. Depending on the outcome of the measurement, then you can apply some unitary operator to the second system in such a way that at the end, the whole process is the identity operator in which you have transported the same state from one place to the other one. So it doesn't happen anything to this state, and this is independent of the outcome. But this is a more general statement in which you say that it may happen that in some occasions, these cellular automata, then we do some measurements, then it can be corrected with some local measurement. And so this means that now we endow our quantum circuit with more power because we allowed to do some other things that before we didn't allow. And so how powerful is now this quantum circuit? Is it more powerful than just a quantum circuit with ancilla or a quantum cellular automata? And indeed, it is much more powerful. And so in fact, you can show, and I will give you a hint of how this works, that you remember the unitary operator that I gave at the beginning. That's the one that I told you that has a depth n circuit. So it's a lower bound n-1 that's equal to n-1, which is able to create GHZ states, for example. Then it turns out that under this setup, it requires a depth 1 quantum circuit. So this can be implemented with probability 1, let's say deterministically in this setup, just having ancillas, applying only one layer of your circuit and measuring, and then applying local unitary operations. Whereas if you don't do measurements, even with ancillas, it would require a depth n quantum circuit. So again, having measurements allows you to, do things that are not possible, and then even change the complexity, well, not the complexity, but the depth of the circuits by a lot. In this case, from something that grows with the system size to something that is completely independent. And so let me tell you what is the idea of the proof. Well, this shows that quantum circuits plus ancillas plus is strictly included in the set of quantum circuits with local operations and quantum communication. So in the jargon of quantum information, that's what we call local operations and quantum communication. And so yes, of course the proof is a bit complex, but the idea is it's relatively simple. So first, you take what is called a locally maximally entangled state. This was defined in this paper, and this is a state of qubits, a many-body state that has specific property. This specific property is that just by local operations, so acting on a system on an ancilla, then you can create a maximally entangled state with the ancillaries of the system. So again, it's a state of your system that if you put ancillaries and you act locally, now if you cut here, they are maximally entangled. So most states are not locally maximally entangled because it's impossible just using local operations to maximally entangle. Product states, for example, are locally maximally entangled, and it's trivial, but if they are a little bit entangled, it's very difficult. But there is a big set of states that have this property. And now you can use these states to teleport, to kind of apply a unitary operation on the state that you have in your system. So the state that you have in your system is this green one. That's the one that you want to apply the unitary operation. Now you have the state. Actually, this state now, since it's locally maximally entangled, it's itself a choice state, so it can give rise to unitary operations. So in fact, if now you would measure the red ancilla with your system in the Bell basis, then you will have some random outcome. And then what will happen is that you will have that the state of these particles here, like in teleportation, will have changed depending on the outcome. But it turns out that now, if this is an LME state, and you put an extra condition, is that the unitary operation corresponding to the choice state is a Clifford circuit, then automatically you can show that you can undo this result of the measurement, as I told you before. So it's a little bit of idea. So as long as you can have a locally maximally entangled state, which can be generated with the quantum circuit, and then you do these operations, then you can implement some stabilizer state. And the example that I gave you before is a stabilizer unitary operation, sorry, not state, Clifford unitary operators. Okay, so now this means that in all these setups, for example, then some operations, if you have measurements, they don't distinguish the dimensionality, so they can be performed in depth one. And so for particular implementations of quantum computers, that's very useful because there is a lot of, if you have some non-local operations that you have to apply in the circuit for doing a quantum computation, then there is a lot of overhead. And what it shows that in some cases, if you're able to perform measurements, that you can get rid of this overhead. This also changes the classification of phases that I was mentioning before. So now you could define an equivalent relation saying that two states are equivalent if they are related by a low depth quantum circuit plus local operations and classical communication. And so what happens in that case is that now there is just a single phase in one dimension. So independent of the degeneracy, all states are connected to each other. So all these phases that we had before collapse into a single phase in one dimension. And in two dimensions, it's even more interesting because several of the topological phases become trivial. So for example, toric code, double models, and many other topological phases then become trivial, meaning that they can be created starting from a product state, just one depth one quantum circuit, and then some measurements. And so some recent work by Vishwanath, so they have shown that actually now there are some phases, topological phases that cannot be created in this way and so on. So they have a full classification into dimensions. So it can also classify unitary actions, and there is a lot of work that is being done at the moment in that context. So I want to finish up in my last 5 minutes and now extending the notion of quantum cellular automata, quantum circuits, and tensor networks, but now to arbitrary channels. So this means that now we are not interested only on unitary dynamics or unitary evolution, but a more general evolution that is allowed by quantum physics. These are quantum channels. So we have again a lattice, and we have a physical action that now transforms density operators into density operators, and we have a new state, a new density operator here. And so now the question is that this channel, which is a completely positive map, trace between completely positive map, then, I mean, how do we impose that it's a quantum cellular automata or some kind of locality? And now there are many ways of doing that. So for example, one is the one that I told you before. We can impose that this causality preserving quantum channel, that for example, if you act in some region B, then you apply the unitary operator, and then you measure any observable in A that's independent of what we have applied in this region. Okay, so this means that, I mean, you cannot somehow send signals from here to here by unitary operation by doing something here and then applying your, let's say, your quantum channel. So this is a notion that is related to causality. You can make another notion. You have another notion that is related now to locality. So what you can impose is that you have a product state between two regions, this A bar and B bar, and then you apply the quantum channel, you look at between the correlations or the correlations between some regions inside A and some region inside B, that there are no correlations established. So this quantum channel then cannot establish some non-local correlation. So this is what we call locally preserving quantum channels. So I have here a little bit more of explanation of that, but that's not so important. And so I will now say that, okay, so these are two different definitions, one based on locality, one based on causality. And it turns out that if this is not a channel, so if this is a unitary operator, this gives rise exactly to the same definition as we had before, the definition of quantum cellular automata. However, if these are channels, so these are more general than unitary operators, then they give rise to different definitions. So these definitions of keeping locality and causality are different. Now, other possible definitions is Steinbring's dilation channel. So this means that you can always create a channel just by define channels just by adding an ancilla, acting on the system with ancilla, and then tracing the ancilla. This gives rise to some trace preserving completely positive map. And so you could define a channel in which you do this action of adding ancillas, but now the unitary operation that you apply on the system and ancilla is a quantum cellular automata again. So this is what is called Steinspring dilation of a channel. And this would be the Steinspring dilation that can be obtained through a quantum cellular automata. That's another definition that makes sense. Another definition is, of course, tensor network channels. So this would be channels that are defined in terms of tensor networks, and that these tensor networks have the property that I mentioned before, simple. And so now you can make a connection between all of them. And this is the result. I just show you the outcome is that the causality preserving quantum channels include all the rest and strictly include all the rest. Now, the tensor network quantum channels are different from the locality preserving quantum channels, and the dilation, Steinspring dilation quantum channels are strictly included in both of them. So you can have now, before for unitary channels, all these were the same, but now you include non-unitary, so I'm still trace preserving completely positive map, then there are different definitions. And I don't have time to talk about that, but the reason for that can be traced to the fact that the causality preserving is a convex set. Okay, so you take two causality preserving and you add them, there's still a causality preserving, whereas the locality preserving is not convex. So you add some two locality preserving, then you can create something that is non-local. And that's the reason why this includes, and I mean, there are some other statements that I could make, but anyway, so that's the definition. So let me just finish up talking a little bit about the area law. So now you can also think about how channels, the channels that I defined before, act with respect to the area law. So you start with a product state and you apply a channel. Do you create a lot of entanglement or very little entanglement? And this amount of entanglement is typically measured in terms of the area law. And so you can ask whether now you apply a channel to a product state, it will create not entanglement, but mutual information, because we're dealing with mixed states between the region and the rest, that is upper bounded by the perimeter of the region, like in the area law or not. And so it turns out that then these locally preserving quantum channels and tensor networks obey the area law in this case. However, the causality preserving don't obey the area law and can create volume kind of mutual information. And indeed, I mean, one can do it. I mean, you can show that because one can find an example. And this example is built just by making convex combination of this causality preserving, and then you put many that create a lot of correlations. Okay, so with that, I would like to conclude. So I'll be talking about three notions of unitary, let's say, operations that somehow are related to locality and causality, quantum circuits, quantum cellular automata, and tensor networks. We have then seen that, I mean, tensor network include the quantum cellular automata includes quantum circuits. However, if we endow them with ancillas and tensor networks, we restrict them by putting some extra technical condition, they are exactly the same. Then we have extended quantum circuits and all of them to include now also local operations and quantum communication. And then we saw that they are much more pureful, and these have some implications in quantum computation, but also in the classification of phases according to this NEEP criterion. And then I have extended quantum circuits to channels, not imposing that they are unitary. And then we saw that there are many definitions, but in particular two that are very logical, one based on causality and the other one based on locality, give rise to different definitions, and then connected them to tensor networks and proving to area laws from them. And I mean, some things that we are currently studying are connections of quantum circuits with local operations and classical communications and tensor networks, because one can see that they are more powerful, but they are still tensor networks. However, they don't have these simple conditions. We would like to characterize them in this way. And with that, so I would like to thank you for your attention, and I'm very happy to answer questions.
Thank you very much for very beautiful talk. So it's time for questions. Okay.
Is there any necessary for the two equivalent states is close in the distance of the state space, like fidelity or something like that, in the sample limit?
That it's close?
Yeah, close in, sorry. Is there any necessary for the two equivalent states is close in the distance on the state space, like fidelity or something like that, in the sample limit?
Close in the distance, you mean like a close set or close near to each other?
Like the fidelity or something like that.
Oh, that is close in distance. Ah, I see. No, it's not necessary. No. This test could be very different and could have even a very small overlap. So in fact, you take a state and then you move it to the right and it's not translational invariant, then the next state that you will have will be equivalent with this equivalent relation, however, will be orthogonal in the thermodynamic limit. So it can be completely different. Or you take the state 0, 1, 0, 1, 0, 1, and then you shift it to the right, it will be 1, 0, 1, 0, 1, 0, which is orthogonal to the original one. So these are equivalent, but they are not orthogonal. So they can be very different. So the notion is rather if those states have similar properties and kind of locally, okay? So that if you look at correlations, then they are basically the same. The correlation length is basically the same and things like that. That's the physical idea behind it.
I see. Thank you.
Yes.
Okay, thank you very much. I wanted to ask you something. Maybe I just missed it. So when you leave the unitary realm and you enter the channels, you are moving into like inference or kind of statistical inference point of view. So how can we talk about causality there? Like, could it be that, for example, a channel could have a unraveling in terms of, I mean, the channel could be like causally preserve causality, but would have some kind of unraveling in terms of causal violating underlying mechanisms or something.
Yes. This is indeed, this can happen. So this is why, I mean, you would like to say, what is the most general channel that preserves causality? And this is the most general. And then maybe that's not satisfactory. And because you would say that, okay, so in physics, you would not only would like to preserve causality in the channel, but you would like to say that the implementations of this channel, what you say in unraveling, there are many unravelings for channels, but that there exists at least one that's still composed of some actions which are causal. And this would be then the definition, this would, so to what you say, would correspond to the definition of Stein-Springs dilation. So this would be that there's a Stein-Springs relation, which is a unitary transformation that concerns causality. And indeed, what we show is that this happens. I mean, what you say exactly happens. So there are some channels that you define naively, only imposing that they fulfill causality. Then you want to implement them in the lab. Then at some point you will have to violate this causality, even though the result of the channel does not break any causality, that does not have any, you cannot signal with that.
Tasaki-san?
Yes, Ignacio, yeah, thank you very much. It was a great talk. And I was excited about this LOCC part, but let me be conservative and ask a question about the first part. So I failed to understand the definition of simple tensor network. So is it something, so how should I receive it? Is it something technical and it's true for almost everything, or is it some special relation?
Okay, so it's yes, so it's something technical, and it's let's say the set of tensor networks that fulfill that would be zero measure. So it's a very special condition.
Okay.
So most of them don't fulfill it. So indeed, so you would take now a random unitary tensor network, and then it would not be a quantum cellular automata, would not respect this. So you have to be very special. Now, except in one dimension. In one dimension is different. So in one dimension, so what we proved some time ago is that you impose that you have a tensor network, an arbitrary tensor network, that on the one hand, it's unitary, and on the other hand is translational invariant, then most of them fulfill that property. It's a generic property, but it's only in one dimension. In higher dimension, it turns out that it's not generic. And so the idea, a little bit the idea, if you want, is that you say if you have a tensor network, this is U, and then you put U dagger, which is another tensor network. This should give rise to the identity, right? You multiply U dagger. This has to be equal to the identity. So this means that at the end it has to be some, let's say, identity is a tensor network, which is a product tensor network. This identity on the first qubit identity. So by multiplying these two, you have to get the identity, and this could happen in a global way, or this could happen in a local way. It could happen that each of them, somehow, these tensors give rise a little bit to the identity. And this is what it happens. That's the condition, that almost locally, they kind of disentangle. And yeah, so I cannot express it in more physical terms, but it turns out that in one dimension, it's very typical for translational invariant, and in two dimensions, it's not.
Okay, so you cannot even approximate a general tensor network by this simple tensor network in higher dimensions.
Okay, this is a good question. So I'm saying that this zero measure, but there might be maybe that you can approximate them closely. Okay, like I mean, the spread of natural, sorry, of rational numbers is zero measure. It's not dense, but still you can approximate them, you know. So it can happen still.
But that's what I expected when you first said that it's zero measure. But when you explain this idea that this U equal 1 must be satisfied locally, then in higher dimension it could sort of escape in a global manner. Then you cannot even approximate. That's what I thought. But anyway, okay. Thank you.
Okay, so any other question?
Yes. Thank you for the talk. So there's a paper by Beijing and Xiaogan Wen in 2015 discussing like local stochastic circuit instead of local unitary circuit. So they replace quantum circuit by some invertible but positive, just invertible operator, and they claim that any GHZ like state can be arbitrarily close to the product state in the stochastic operation, but they claim that the claim is topological order stays. The classification of topological order stays under stochastic operation, even it is non-unitary. So I'm wondering if it could be like something between QCA and QC plus LOCC, because it collapses GHZ state, but still seems not strong as LOCC.
Yes, so I'm aware of this paper. However, I think that the setup, as you say, is different. I mean, they don't allow for communication, and so you would like to implement that. Then by having a operator which is invertible but not unitary means that you will have certain probability. So things happen with certain probability, and in fact, at the end, the probability will be typically exponentially small that something occurs. And actually, there are many papers that have now follow this line of research in which they assume that they are making measurements, but not reacting with respect to the measurement. So what changes in our case is they say we make measurements, but we are allowed that, since we know what is the outcome of the measurement, to apply local unitary operations. And this is what, as you say, I mean, changes from the fact that you cannot create topological states with these stochastic methods, and to the one in which you have classical communication. Yes. So I don't know what would be an intermediate step, because of course what you could do is that you could restrict the classical communication to classical communication only between nearest neighbors. Okay, so then the outcome of your measurement, or the action that you do after the measurement, only depends on the measurements of your nearest neighbors. This could be a possibility. However, it's shown, it can be shown that then this can be reproduced with ancillas. So this will not change the class. So here it's very important, if we want to change the class, that there is classical communication that is not only nearest neighbors, that is classical communication. So in other words, when you measure all your ancillary qubits, then you have some outcomes. So each qubit, the unitary operation that you act on each qubit, depends not only on the outcomes of the nearest neighbors, but all the outcomes of the other ones. That's what changes. And so I don't know how to make something in between the two, as you were asking, in such a way that you will have, let's say, something maybe sensible, that's not dependent on probability, but still, it's still different.
Thank you.
Ignacio, I have one question about this causality preserving quantum channel. So there, in the final part of your talk, you mentioned it can be also volume law like behavior. And so for example, we know that starting from direct product state and time evolves by standard, chaotic Hamiltonian, we have like summarization, and that gives, for example, entanglement increases linearly. So is this a volume law you mentioned, or something different?
Yes, indeed. So it turns out that so you can break the area law. So meaning that you can create even volume law, not entanglement. This is mutual information, because these are channels. These are not unitary transformations. You start with a product state, you apply a channel, and they create a mixed state. And now this mixed state, then you can measure the correlations in terms of the mutual information. And if you look at whether the mutual information fulfills an area law, then we know that, for unitary channels, it always fulfills an area law. However, for this causality preserving, you can break the area law. So this would violate what you say. And the reason for that is hidden in the fact, I think that there was a question before, that this definition by causality is not strong enough to prevent from creating this amount of correlations. And the reason is because this a causally preserving channel is a convex set. So meaning if I have a causally preserving channel, something that does some unitary transformation, then I can build now another causal channel just by mixing it, two of them. But I can also mixing by somehow correlating classically some things that are very different. And this, give rise to this creation. By mixing many of these channels, you can still keep causality. However, you can break and create a lot of mutual information in a single step. That's the reason behind. So I had the example, but I don't have time to explain this example of how you construct a counterexample of something that violates the area law.
So so the example you mentioned is different from standard with the nearest neighbor, like in interaction and the time evolution.
Right. It's exactly. So it's a channel. It's something which is defined mathematically as something that transforms density operators into density operators, is linear according to the laws of quantum, fulfills all the laws of quantum physics, is linear, and then you impose that there is causality, so that you cannot signal with that.
So
and you impose these conditions. These are the only conditions. Then you can see that you can still violate area law.
Also, in the final part of in this final slide, you mentioned the connection between QC, LOCC, and the tensor network, as also in previous questions. So if we take, for example, like mirror, like tensor network, is it possible to have just one layer or finite layer description in terms of your measurement and ancillary?
Okay, so right, so I don't think so. I think that you would need, for a mirror, you need okay, so that's a good question. So for a mirror, probably to create some of the GHZ states, you would need, it doesn't come directly from my mind, but a log nth circuit. But there, of course, you're playing with the role that if you go from the mirror, you go to the top, then it's like doing a very non-local operation, right? Because on the top of the mirror, like in normalization, then you're acting on the whole right and the whole left. So with that, you can circumvent the fact that you need a depth n layer by having only log n layer. And but what I'm not sure, and that's a good question itself, is if you have that power of putting a mirror, that you could create all possible tensor networks, not tensor networks, all possible quantum circuits and local operations and classical communication. So I don't know. I don't know the answer to that.
I see. Thank you very much. Okay, so
Okay,
any
thank you.
other question? Okay, or are there any question for online participant? Okay, so we had quite a lot of questions. So thank you very much, Ignacio. Wonderful talk.
Okay, thank you very much. Thank you.